The Adventures of Mr Tompkins was created by George Gamow, the renowned physicist who first proposed the physical model of the universe known as the Big Bang Theory. He is perhaps best known around the world for having created the curious and lovable bank clerk, C.G.H. Tompkins, a bank clerk who dresses as if he's the president of the bank. His understanding of mathematics is limited to the operations of addition, subtraction, multiplication, and division, of which he uses only 2. Nevertheless, he has a passion for attending science lectures. After the lecture, he goes home to bed and dreams that he has been transported, pajamas and all, to the time and place where the celebrated scientist lived and worked. The next morning, Mr. Tompkins wakes up enchanted by his new understanding of science. Igor Gamow is George Gamow's son and the creator of the Mr. Tompkins film series. Igor has worn many hats. The white hat of a cowboy hero, the black hat of the villain, motorcycle hat of a White House courier, and a feathered hat as a member of the National Ballet Company. Today, he wears the hat of a professor.
Good evening. Tonight's lecture is entitled Einstein's New Theory of Gravity. Any and all interactions on heaven and on earth, which includes trains, planes, and exploding stars, could be all explained with the 4 fundamental forces in the universe. These 4 forces are, firstly, gravity. The second fundamental force is electromagnetism. The third and fourth are nuclear forces, the weak forces, which accounts for radioactivity in cobalt, uranium, and then finally the strong nuclear forces, which are the forces which hold protons and neutrons together very, very tightly. And if they are split, fissioned, then you have, of course, atomic energy. Now, of the 4 forces, the odd child is gravity. Because although gravity is millions of times weaker than the other 3 forces, on the other hand, it's significant for large objects. The gravity on the sun, given that you could stand the temperature, is huge. The gravity on Earth is large. And even for objects as big as me, or as small as me, gravity is significant. Now, I can walk in the X direction, the Y direction, but I cannot go in the Z direction unless I possibly can hop a little bit.
I have no problem with the Z-axis.
Well, my beautiful aerialist is actually not weightless, but Marilyn Monroe is weightless. Well, not for very long, a fraction of a second. She was obviously on a trampoline, and the photographer caught her just at the apex of her jump. But weightlessness is really very important in order to train astronauts to be living in shuttles and space stations. And so normally what they do, they'll take an astronaut dressed fully in all the suits and boots and helmets, put a buoyancy compensation vest built into the suit, and put them into a huge swimming pool where they're all floating around at 0 G with a module which they're trying to assemble and disassemble. Another creative way of creating 0 G or low G is by using what's called a vomit comet, which was originally a KC-135 military plane. And you take a group of people, all with pads in the compartments, and the plane literally falls out of the sky. And for 25 seconds, it is weightless. And you can see the people moving around, apples floating around, magazines floating around, bears doing somersaults. It's absolutely a ball. Now, one of the greatest scientists we've had of the last century and of this century is Stephen Hawking, a theoretical physicist who's been confined to a wheelchair. What a kick it would be to be able to shed his wheelchair, if only for 25 seconds. And so recently he was in a vomit comet, and you see him now floating for the first time absolutely effortlessly. Now, Hawking is a real scientist, but he's playful. And one of his favorite TV programs is Star Trek. And Star Trek invited him to one of their episodes, and now you can see him sitting at a table in the Enterprise, along with Newton with the long wig, Einstein with the bushy hair, and then Hawking. It was sort of a life dream. Now, let's get serious about gravity. The first person who really studied gravity sincerely was Galileo. And his most famous experiment, allegedly, the experiment he did, because there's some doubt that he ever really did this experiment, that he climbed up to the top of the Leaning Tower of Pisa. Apparently, he wasn't leaning so much at that time, with an iron ball and a wooden ball. And the idea was, if he dropped it from the top of the tower, which would hit first? Now, when he did the experiment, the alleged experiment, everyone was astonished that they hit simultaneously. But not Galileo. He knew it. There was no problem. The second experiment he allegedly did, there's always a little doubt whether he dry labbed, but apparently he was in a cathedral attending Mass. And maybe he wasn't paying full attention because there's a large chandelier, and the chandelier was swinging in the breeze within the cathedral. And Galileo, being Galileo, decided to measure the period, the length of time from one extreme swing to the other. Now, of course, they didn't have a wristwatch, he didn't have a water clock or a sundial. So Galileo, while being in the cathedral, watching the swinging chandelier and measuring its period, discovered that the period was a constant. Now, if my beautiful aerialist was in Italy, in the same cathedral with Galileo, would he have been able to make the same discovery as when he was measuring the chandelier? Yes, you say. No, I say, because remember, he was measuring his pulse, and I would predict Galileo's pulse, his pulse, like mine, would probably certainly increase off the chart when this lady would swing by. In 1642, Galileo, after a very, very interesting career, died. But all is not lost, because in 1642, Isaac Newton was born. And Isaac Newton will become probably the greatest scientist of all time. Now, Newton is famous for his apple. And allegedly, here's another one of these stories which probably is not true, but Newton was sitting on an apple tree. And while he was sitting there, this apple fell and bonked him on the head. And eureka! He immediately began to think, the Earth's gravity, what we call gravity, pulled the apple down off the tree, just like the Earth's gravity pulls the moon towards it, and that's why the moon is in orbit. He then went and did a series of equations of motion, in which he could describe exactly the motion of the falling apple with the motion of the falling moon. And therefore, in one single wonderful streak, he was able to combine terrestrial mechanics with stellar mechanics. Because everything that happens on Earth, he could predict would happen in the heavens. He became so famous for this that he was almost like a rock star. Probably not during Newton's time, but a little later, they had something called the Gedanken experiment. Gedanken is the German word for thought. So maybe Galileo, when he was dropping balls from the Leaning Tower of Pisa, actually did a Gedanken experiment. So Newton would, with his laws of motion, would say, if you took an apple, Newton's favorite apple, and you threw it in the void of space, where there was nothing there at all, no planets, no stars, only the dark voidness of space, he would predict by the first law of motion that that apple would travel in a straight line forever, never changing. Now, let's put Jupiter. Now we have the apple moving towards Jupiter, and the apple now has a problem, because the apple wants to go in the direction that I threw it, but it's also being tugged by the gravity of Jupiter. Now, if the numbers were all correct, and the distance from Jupiter and the velocity of the apple was just the right, correct numbers, then the apple would go into orbit. And you have orbital mechanics. Now, the other experiment, which is the combination of Galileo and of Newton, for instance, if I took this apple now in this auditorium and I threw it as hard as I could out to the audience, how long from the time the apple left my hand would it hit the ground? Well, with the work of Newton and Galileo, you don't have to do that experiment, because since the apple is continually being pulled by the earth, even while it's traveling forward, it will hit the ground at exactly the same time as if I dropped the apple here and it hits the ground, and I could just measure that. Now, if I had a gun, thank you, and I was in the field with my trusty BB gun, and I would shoot the BB straight across the field, or I would drop the BB here, the BB in both cases would hit the ground simultaneously. Now, Einstein's favorite Gedanken experiment is what is now called the Einstein's elevator. So let us go back to the void of space. Nothing is there at all, except one elevator, looks like a rocket ship, and the elevator is motionless. But now we'll do the following experiment. We will start accelerating the rocket, the elevator, and the observer looking through the window will see the floor coming up, coming into contact with the floating apple, and as far as the scientists know, all at once gravity has been restored. There is no experiment that anybody could do to distinguish between the acceleration of the elevator or the gravity you feel on Earth. That's really very interesting. Now, if we go back, and I'll take my apple, give it to one of the intrepid scientists, and the two scientists will play catch. The scientist on the left will throw the apple to the right, back and forth. But what you would see as an observer, as the apple went from left to right, it would appear to be curving downward. Well, you'd say that's not really true. It's only because the elevator has moved up. But Einstein says it doesn't make any difference. Now let's do another experiment. And this is a mind-blowing experiment. Let us shine the light beam, and if you had careful measurements, the light beam would follow the same path as the apple. It would be curved. And you would say, how could that be? And when Einstein first produced this paper in 1914, people were just unbelieving. Because is it possible that light will be affected by gravity? And of course, what Einstein said is that it's a time-space curvature. You can think of space as a fabric, and as a large body, meaning something like acceleration, it deforms that fabric, and we would interpret it as gravity. It's a wonderful, wonderful concept. But then people started to worry, well, how can you have space, which is nothing, and how can you curve nothing? Is there any experiment you could possibly do? Sir Arthur Eddington, he wasn't a sir at that point, decided that he would test Einstein's theory of curvature of space, space-time fabric. And so he devised the following experiment. If you take two stars, now if we look at these two stars, and of course tens of thousands of light years away, if we look at these two stars from Earth, they're fairly close to each other, and we know what the distance is, because we can measure the distance, we can measure the angle between them, therefore we know the distance between the two stars. Well, let's say now that we take our sun, and we take our sun and put it right smack in between these two different stars. What would you see? Well, you wouldn't see anything. Why? Because the sun is so bright. You don't see stars in the daytime. You only see it when the sun's not there. So how could you get rid of the sun light and not get rid of the sun? Aha! Eddington was very clever. In Africa, there was going to be the total eclipse of the sun. That's when the moon passes between the earth and the sun. Therefore, you have this black disk, and you have night. So he did the experiment and measured the distance between the two stars, the way I just told you, with and without a sun. And Einstein had calculated what degree difference would be because the light coming from the stars passing by the massive sun is bent, just like the light was bent in Einstein's elevator. And the number that Sir Arthur Eddington got was exactly the number that Einstein had calculated. Now I have two more stories. One story is they asked Einstein, what if Eddington didn't make that measurement? Maybe it didn't correspond to your equation. And Einstein, of course, said, I would have been very surprised. Just like Galileo would have been very surprised if the two balls hadn't hit the ground at the same time. And the last story, which is documented, there was a reporter who came to Eddington to write an article in the London Times about this wonderful experiment. And the reporter asked Eddington, he said, I understand that there are only 3 people in the world who understand Einstein's theory of relativity. And Eddington turned, he said, really? Who's the third? And the reporter's a little stunned, but of course Eddington said, ha! He knew Einstein understood it, he knew that he understood it, and he was curious about the third. So ladies and gentlemen, that's my take on the wonderful new theory of Albert Einstein's gravity. And good night.
Where am I?
Where indeed? Where indeed? Would you believe outside our solar system?
Outside the solar system?
Yes, on a small asteroid, some 5 miles in diameter. Behold!
That's impossible!
The Sun and the 9 planets. Well, 8 planets. Pluto, after recent discoveries of many objects similar to it in composition and mass, was demoted to the newly created status of dwarf planet in 2006, a rank it shares with 4 other celestial bodies. But I digress, as we scientists often do.
Amazing, but hey, I know you, you're...
Oh, pardon me, sorry, but I'm always mistaken for him.
Huh. But I could swear...
Oh, I'm sorry, Mr. Tompkins. Just a little private joke at your expense. Yes, you are quite right. I am Professor Albert Einstein, but you may call me Al.
How do you know my name?
I was a friend of your father, George Gamow, physicist, cosmologist, and author of the Mr. Tompkins books series.
Book series?
Yes, Joe, as we called him, also developed the Big Bang theory of the origin of the universe. We worked together on several projects. Why, I even met your brother Professor Igor when he was only 4. He just wanted to be a cowboy. How amusing that such a famous scientist as George Gamow would have a cowboy son. What is the matter?
I'm not a real person? Just made up?
Yes, lad, you're only a fictional character, but follow Dr. Einstein's advice and you will be fine. So tell me, have you any questions about Professor Igor's lecture?
I once saw a movie about a black hole. If gravity's the weakest of the universe's 4 forces, how can a black hole's gravity be so strong that not even light can escape it? Are there 2 types of gravity, like the strong and weak forces inside the atom?
No, Mr. Tompkins, there is only one gravity, but the strength of the gravity is directly proportional to the mass divided by the volume of the object, which we call density. Watch closely, my boy, as I pluck Earth from its orbit, like so. Squish it down to the size and volume of a cherry, just incredibly increasing its density, then shrink it to the size of an ant. Finally, place you on the surface of the cherry. Try as you may, you cannot move even 1 step due to the huge gravitational force of the cherry.
Okay. Already I get your analogy. I understand your point. Let's see if I can extrapolate from what you've told me, Al. If I inflated the Earth until it was the size of, let's say, Jupiter, I could jump 100 feet in the air since there's so little mass in so large a volume.
Yes, Herr Tompkins, you have the idea, but we would have to use Newton's laws of motion to calculate exactly how high you could jump. But now time to play with our Mr. Sun. Let's make 3 suns, shall we? Then tightly compress them until they are the size and volume of the Earth, again enormously increasing the density, and Achtung, a black hole. Its gravity is so great that nothing can escape it, not even light. Well, almost nothing. Stephen Hawking proposed that due to a quantum fluctuation, a temporary change in the amount of energy in a point in space, a little matter can seep out of a black hole. As a result, the black hole shrinks. The decreasing volume of the black hole increases the radiation seepage, thus speeding up the evaporation of the black hole until it eventually disappears. The radiation has been named, surprise, surprise, Hawking radiation. I must admit that in my day I thought the idea of a black hole was absurd, but never let it be said that Einstein is stuck in his ways.
Perish the thought. Another question, if I may, Al.
Of course, but hurry, you may wake soon.
I have down in my lecture notes, let's see, here it is. With the masses and speeds we have in the solar system, your theory of relativity and Newton's laws of motion are pretty identical. It's only when we deal with huge objects at speeds nearing the speed of light that your theory becomes important?
No, Herr Tompkins, that is entirely untrue. Your notes are simply wrong. Newton believed that gravity forces traveled instantaneously from point A to point B. I, however, have clearly shown that nothing can go faster than light speed. For example, Newton believed if the Earth suddenly moved 1,000 miles closer to our moon, it would alter its orbit instantaneously. Einstein predicted a significant delay before the moon altered its orbit. On a larger scale, if the sun were suddenly to disappear, Newton would predict that the planets would immediately fly off into space at the exact moment the sun vanished.
Could the sun suddenly disappear? 1 minute it's here, the next it's gone?
No, it couldn't, but for the sake of our Gedankenexperiment, let us say it did. Since gravity waves travel at the same speed as light, 186,000 miles per second, it would thus take 8 minutes before we on Earth would see the sun blink.